Hi everyone, welcome to the presentation of our paper ReDro, Efficiently Learning Large-Size SPD Visual Representation. I am Simon Rahman, the lead presenter of this paper. Good image representation learning remains a central issue in computer vision. This is primarily due to the variations such as pose, occlusion, and scale in the image data. A significant amount of research has been conducted for learning good image representation, amongst which symmetric positive definitive or SPD matrix representation has received significant attention. Given a set of image descriptors, SPD representation computes pairwise correlations between feature components. It is also known as second-order features. For effective estimation of SPD representation, matrix normalization is a key step. There are three key motivations for performing matrix normalization. Firstly, SPD matrices reside on Riemannian manifold. Secondly, to battle the Brastiness phenomena. And thirdly, robust estimation of SPD from smaller sample size. However, in the existing end-to-end SPD networks, matrix normalization is a bottleneck due to their use of eigendecomposition. Unlike many matrix operations, eigendecomposition has poor GPU support, and its complexity increases quadratically with the increase of CNN feature channels. Modern CNN, such as ResNet, produce higher dimensional feature maps. Eigendecomposition of SPD matrix produced from such higher dimensional features is extremely inefficient and impractical. Since it is expensive to perform eigendecomposition on high-dimensional SPD metrics, existing methods reduce the feature channels to compute a relatively smaller-sized SPD metrics for eigendecomposition. In this work, we are curious about if the computational challenge of computing eigendecomposition can be mitigated from another orthogonal perspective. A large number of research has been conducted for SPD representation learning, amongst which bilinear CNN and deep O2P are two pioneering methods for learning end-to-end SPD representation. However, the framework of deep O2P is largely followed and continuously improved by subsequent works. Let's have a look at how the matrix normalization is performed in SPD networks. Let's take a look at MP-NCOV network. Given the CNN feature maps, it computes covariance matrix and then performs eigendecomposition. The eigenvalues and eigenvectors are then used for matrix power normalization. Two existing methods propose to replace eigendecomposition based matrix power normalization with approximate matrix power normalization. However, only the extension of MP-NCOV network was successful in using this idea in both forward and backward propagations. Along the line of efficient computation of SPD features, compact bilinear pooling is another group of methods that focuses on estimating compact covariance representation. There are also methods from other perspectives for efficient SPD representation. However, all of these methods generally do not use matrix normalization. Our ReDro is not competing with these methods. ReDro can be embedded into these methods to perform efficient matrix normalization. Inspired by the dropout idea, some researchers extended it for CNN, such as spatial dropout, drop block, and weighted channel dropout. Conceptually, ReDro can be viewed as a kind of dropout but drops relationships in SPD metrics. In our proposed ReDro, given the CNN feature channels, we randomly permute them and divide them into multiple groups. For each group, we compute a small covariance matrix and obtain its eigenvalues and eigenvectors by performing eigendecomposition. Next, we organize them in block diagonal order and permute them back to the original channel order to make the permutation operation transparent to the remaining layers. In this way, matrix normalization can be performed in a more efficient manner. By performing eigendecomposition in a block diagonal matrix, we can effectively reduce its complexity. From a theoretical perspective, ReDro reduces the complexity by k² times. We derive necessary matrix derivatives for end-to-end training of SPD networks with ReDro. They are thoroughly discussed in the paper. ReDro is sensitive to two key parameters: number of blocks in block diagonal matrix and random permutation intensity. The number of blocks in block diagonal matrix decides the percentage of relationship to draw from SPD matrix and the computation savings. Random permutation intensity decides how frequently the order of the channels will be shuffled. The use of appropriate permutation intensity is important, otherwise it may cause slow convergence of training. We test three different permutation levels: epoch level, batch level, and sample level. So you want to keep the same random permutation for two consecutive epochs. We'll express it by EL2. We will use this notation in the following slides. We evaluate ReDro using one scene dataset and three fine-grained image datasets. The details of the datasets are given in the supplementary copy. In our first experiment, we investigate the computational time for covariance estimation and matrix normalization by using or not using the proposed ReDro scheme. The four methods to the left represent the case not using ReDro. The case using ReDro is implemented upon deep COB with various k. From the figure along the matrix dimension, when the matrix size increases to 512 by 512, the advantage of ReDro emerges and becomes more pronounced for 1024 by 1024. In these cases, ReDro is computationally more efficient by 20% to 50% than the non-ReDro counterparts. When the size is relatively smaller, say 256 by 256, ReDro is unnecessary. In this experiment, we apply ReDro at different intensity levels on two networks with different backbones. From the figure, we can see that at many intensity patterns, ReDro is able to achieve better results than the baseline. Here, we use k-value equal to 4. The selection of k-value would be discussed in the following slides. ReDro makes end-to-end training of SPD network more efficient. In the figure, we show that the training time taken by deep COB network with ReDro at various intensity levels. From the figure, we can see that many methods that are trained using ReDro took less training time and better performance than the baseline. Also, ReDro estimates less biased eigenvalues of SPD metrics via block diagonal computation, which improves the quality of SPD matrix estimation. We implement ReDro in typical SPD methods. From the figures, you can see that ReDro is able to produce better results than the baseline, in many cases with less computational cost. We perform an ablation study on block size k with various matrix sizes. From the study, we find that k equal to 4 performs better than others for large size matrices. In conclusion, we propose a novel scheme called relationship dropout. We provide these forward and backward propagations. To demonstrate the effectiveness of ReDro, we conduct extensive experiments with 4 datasets. Our proposed ReDro can be readily inserted into any existing SPD networks without any major modification. In the future, we want to implement ReDro on more SPD networks and gain more insights of its regularization effect. Please visit our project website for code and more details. Thank you and welcome to our Zoom session.